Welcome to this month's Power Hour. So this session is going to be covering VVT diagnostic tips. And it's probably one of my favorite diagnostic routes for many reasons. We get to use a lab scope with diagnosing these systems, and we do a lot of scan tool diagnostics. So all things that are right up my alley. And I want to cover some of the diagnostic tips that I've come to experience and other people have taught me. And there's just good trade practices that we've figured out over the time and different components that we really want to check when we are diagnosing these systems or replacing different components of things that we should do, of best practices of, okay, well, I've replaced one solenoid. Should I do more, or I do a phaser? What all is involved with doing one? Do we have to do anything else along with that? And so with that, we want to cover a lot of things in the shop. We're going to try to actually do some of these diagnostic tips right now with you. Okay, like I said, we're going to get to it right away. We've got kind of a short period of time to cover so much. And one of the things I want to cover right away with VVT is we got to understand a little bit, why do we have it on the vehicle to begin with? And one of those reasons is going to be getting power out of the vehicle. We're also going to try to get fuel efficiency. We can do both of those things with variable valve timing. And with that comes the addition of a phaser to the camshaft. So with these phasers, it actually can unpair the gear from the camshaft and change the timing of that in relationship to the camshaft itself physically. So here we can actually shift that timing, whether we want it to be more fuel efficient, whether we want more power. And one of the final reasons why, you may wonder, why do we have EGR valves sitting on a bench for VVT class? Well, we're actually eliminating EGR a lot of the time with VVT. And so we're going to do that with the changing of the valve timing, and with altering the timing of events between intake and exhaust, we can actually create EGR essentially for the engine with VVT and get rid of the need for the EGR in most cases. And so now there's going to be some diagnostic steps that we're going to have to take along with that. Let's say we've kind of got the idea of, okay, I've got VVT on a vehicle, but what are some of the foundational steps that I need to take? And we're going to kind of pull up the slide here, and I'm going to show you different things that happen. So we're going to have to look at oil level and pressure on the vehicle, make sure that it's good. It's not only good when we're at a cold idle or anything like that. We need to get the vehicle fully warmed up. Now, a lot of the time, we've actually got a vehicle in the shop right now that has had timing components replaced on it, and so it's already had everything done. There's a tick to the valve train on it, and it's because of the oil pressure, but it only happens when it's hot. And so if we have a valve timing issue on a vehicle, since we're covering diagnostic tips, we have to make sure that we check that oil level when it's or the oil pressure, I should say, when it's hot. The other following steps we're going to do is checking for diagnostic trouble codes. A lot of the time, the diagnostic trouble codes are going to lead us in the right direction when we're looking at that vehicle. Then after that, we're also going to want to look at that cam position data in the scan tool when we're looking at it, verify what's actual, what's desired, look at the data. There are going to be times also where we're going to have to use a lab scope to look at the duty cycle and position of the variable valve timing. So whether that is the solenoid that's controlling what's going on, or if we're looking at it from the sensor position of where is the reluctor in relationship to the sensor itself. And we could actually do some compression testing. Let's say we've got a V-style engine where we've got a V6, and we've got a chain going to one bank of the engine, and we've got a chain going to another bank of the engine. If we have one bank that's out of time, we'll actually catch that in a compression test. So if we did a relative compression test with a lab scope, we actually can catch that timing fault. Now, as I said, we've already covered that we need to check that oil pressure when it's hot. And once we've verified that and we're okay with the oil pressure on the vehicle, now it comes time to look at the diagnostic trouble codes with a scan tool. And what you're going to see is on this slide that we've got here, we've got a list of DTCs. It already tells us a good direction to take with the trouble code that sets for the fault. and it can tell us if it's over advanced, if it's actually set back too far, or if there's a correlation issue. Let's say we have a crankshaft in a certain position, it's in time. We have a camshaft that's out of time. Well, if the vehicle does the correct adjustments and analyzing of that, it can tell that the camshaft is out of time, and it's going to say, okay, we've got a cam to crank correlation issue, and it's going to set trouble codes for that fault. If we want to now go from the trouble code into scan data, we're going to look at something like this. This would be a good actual versus desired, and we're going to look at what the angle is. And you're also going to see, when you're looking at actual and desired, remember that these are physical components that are moving. So there is going to be a little bit of a lag in between what's desired and what's actual on there. So don't be surprised if you see a degree or two different when you're adjusting from one position to another. Here would be a good command to a solenoid. So we've got those VVT solenoids on the vehicle. I'm sure a lot of us have already replaced these on, I can think of many vehicles that we've replaced solenoids on. One that comes to mind would be a Ford truck with a 5.4 or an Ecotec GM engine, very common VVT solenoid. Well, in this case, what we're showing you is good data for one of those solenoids. And what you're seeing is in the middle data pit here, that command percentage looks good and flat in between. So when we're controlling that solenoid, it has good stable control of the solenoid. Bad control of the solenoid would look something like this, where we actually can't hold it steady. The solenoid is for some reason failing to hold it in position. Now, whether that's the solenoid or possibly a phaser that can't hold position, we're going to have to dig into that. But first, now we know that, okay, by the command that I'm looking at, it can hold this one solenoid just fine, and it's not actually controlling the other solenoid fine. Now, with that being said, that's all easy and good when we're talking about it on a slide. It's another thing to go on the vehicle and actually look at that scan data. So with that in mind, we've got a Chrysler 200 in the shop right now. We're going to go on the scan tool, and we're going to actually look at some data on this, look at the scan data for VVT, and we'll go through the PIDs that are on the vehicle. All right, Corey, you can start the vehicle for me, please. All right, we've got the vehicle running. I've got the scan tool already hooked up. We had it keyed up, I identified the vehicle. And now we're going to go through the data. You can see that we don't have a specific spot where it says, hey, we can go to timing data. So I'm going to go to live data. And once we've got the data selected, it's going to take a second to load all of the PIDs. You're going to see in a second that we've got a lot of data to cover in the vehicle. I'm going to start scrolling through here, and like I said, it depends on the vehicle of what cam and crank PIDs we're going to have. And so I'm going to scroll through, and I'm already pretty familiar with this platform. We're actually not going to have desired and actual on this vehicle itself. We are going to have some cam and crank sync PIDs though, so I'll just keep scrolling through. Another thing to keep in mind is, like we said on the PowerPoint, we've got an oil pressure that we want to make sure we've got good oil pressure to the solenoids. Here is a good place to double check that as we get the engine hot. And if we keep scrolling through, we're going to get to cam and crank. So here are the cam and crank sync. And if we have any faults at all, it's going to say true to having a fault, and we're going to be in a limp status. And also, it's going to tell us, is the crank signal missing? No, it's not. Yes, it's in sync. This is very typical for Chrysler. So as far as scan data goes on this vehicle itself, this is what we're looking at. We're looking at crank signal missing, crank sync state, and do we have a fault in the system? Other than that, there isn't a desired and actual on this platform itself using this tool. So we're good with scan data. We've got no trouble codes. The scan data is okay. And with that, we're good to shut the vehicle off. Corey, you're fine to shut the vehicle off now. And then we'll go back. So coming back from the scan tool now, we've kind of looked at some of the scan data, and you can see just from the example we showed on the PowerPoint to the vehicle that we've actually got in the shop, the data PIDs vary, right? So we want to make sure that we look at what's available for our vehicle, and I'm going to try my best to analyze what data PIDs are there. If it just says cam and crank sync, if it's got the actual and desired. Now, one thing I wanted to cover though is where does all of this information actually come from? And it's going to come from the sensors. So these position sensors, I've got a couple right here. We've got cam and crank sensors, and they actually tell the relationship based off of this reluctor on each gear that we've got. So we've got a crank gear, and we've also got cam gears, and we're going to have a reluctor on each one of these shafts. So whether it's actually on the gear physically or if it's mounted on the shaft, we're going to have a point of reference. You can see 2 small tabs here and then 3 small tabs on the bottom of the phaser. Now, all of these are going to kind of vary vehicle to vehicle, but they are going to have a point of reference to look at, and the sensor is going to be watching that. One of my tips here is that we got to make sure that we're putting in a quality sensor. Here we've got one of our sensors that is a quality sensor, and it can determine the rotation direction, positioning, everything like that with how the component is actually rotating. There are some sensors out there that may be a little bit more inferior, and they lack some of the positioning details to it. So it might not be able to tell, okay, what direction did I rotate? And that can be important, especially in applications like on a Nissan vehicle, where we've got to make sure that the sensor is built correctly to monitor position and where it's rotating and how fast it's going. Now, I want to actually dig into those sensors a little bit more. We're going to go back to the presentation. I'm going to go to the slides now, and we're going to look at the first style of sensor. So the first style of sensor is going to be a 2-wire variable reluctance sensor. A couple of the key factors here are going to be how fast is it rotating. There is a magnet in this sensor, so how strong of a magnet is internal to this. Again, this is where a quality sensor comes into play. We're going to have coil inductance into this sensor, and one of the key things for a technician, if we're trying to diagnose or repair these, is to keep in mind the sensor gap. We've got to make sure these things are mounted properly. We don't have any corrosion. I can think of on a timing cover where if you've got corrosion on the timing cover, you install a new crankshaft sensor. You can actually have it shimmed out far enough from corrosion that we don't pick up the crankshaft reluctor good or well, and that then all of a sudden we have a signal that we're not looking for, and it's going to sometimes pick it up and other times not pick up the signal properly. The next type of sensor is going to be the 3-wire digital sensor. Now this is going to be the sensor that we've got on the bench right here. So we've got these 3-wire sensors. These are going to be a Hall effect digital sensor, and this is going to be what we're seeing on most all new vehicles, but we do actually see the 2-wire variable reluctance sensors still in play. The big difference between these two signals though is going to be the 2-wire variable reluctance sensor will look like a sine wave, like what we see at the bottom of the screen going into the Hall effect sensor. The 3-wire Hall effect sensor takes what would have been the 2-wire variable reluctance signal and adds another device to it. So when we've got the Hall effect device and a transistor internal to the sensor, we now output a square wave signal. Now again, this all is well and good when we cover it in a PowerPoint, but I want to actually show you what it looks like on the vehicle, and so with that, we're going to look at a diagram right here. So we're looking at the PowerPoint a second. We're going to look at what the pinout would be, and I'm going to hook up with a lab scope to this Chrysler that we've got. We already did the scan tool. Now we're going to look at it with a lab scope. And with the lab scope, if you look at the 3 pins of the crankshaft position sensor at the upper left of the screen, I am connected to the CKP signal, which is going to be the signal wire for the crank signal. And then we are going to go to the camshaft position, and we are going to go to the CMP signal to wire. So with these two different signals, I've got them on channels A and B, and we're going to hook up. We're going to make these connections, and we're going to analyze the timing on this vehicle. Corey, could you start the car up for me again, please? So as I was saying, we're hooked up to the cam and crank. We're on the signal wire. So I actually already made these connections. And if we look at this signal here, the channel A, which is the blue channel, is going to be our crankshaft signal. Channel B is going to be the red cam signal. So now we've got our cam and crank. This is only a 4-cylinder engine. We don't have multiple cam signals on here as far as bank to bank or anything like that. So if I'm just looking for, let's say I've got a correlation code, I'm probably going to just look at a couple of PIDs and see if I've got a correlation issue between those two things, the cam and crank that are saying that there's a correlation issue. Now, when I look at this screen, the way that it's going right now, I've got on a really big time base, and also the voltages, I would say, are a little bit off. So we're going to adjust these voltages down a little bit. If we remember, these are 3-wire Hall effect sensor. And so I'm going to adjust these into a range that I think will work pretty well. Now I'm in a pretty usable place where I can look at these signals, I can analyze it pretty closely. You may be thinking, well, the screen that I'm seeing right now, it's moving around a lot. I can't really tell exactly what's going on. Well, with the lab scope, we can do different things to stabilize this waveform. I'm going to select a trigger here, and I'm going to do it for channel A. And that's a good spot for the trigger to begin with, actually. So now we're recording pages and pages of the lab scope information here, and I'm going to pause that signal. So once we pause it, it's paused now. I've got 17 pages to look at. Let's say I had an issue with the vehicle. I can actually scroll back through the pages and figure out exactly where that damaged reluctor was. If I need to zoom in for more clarity, I can also do that. So let me say I want to look at what does 1 revolution of the crank look like. Well, we're looking at the crankshaft here in relationship to the camshaft signal. And now I can see basically my sync is going to be the missing teeth on the crankshaft signal, on the blue signal. And that tells me that I'm at 1 engine revolution between the missing teeth over to the missing teeth. If I'm trying to look at a known good waveform that someone has sent me, this is what I'm going to do. I'm going to measure off of those values there. I'm going to say, okay, well, my missing tooth is here. The camshaft should be, looks like, 10 or 12 teeth off to the right. The known good said I'm supposed to be here. If my waveform doesn't match that, it's going to be out of time. This is how we know, okay, if you're referencing off of a known good, how do we tell? Well, I'm going to measure the teeth off of the crankshaft and look at the relationship between cam to crank. Now, you may be wondering also, I said, this is making a square wave signal of the teeth. Those lines pretty much look like vertical lines on the crank. Well, if we keep zooming in, I'll zoom in really close here, and you're going to all of a sudden see there's a lot of clarity to these teeth. We're zoomed out at a very big time base to look at so many teeth to see if there's any intermittent issues. As I zoom in, we can see all of the detail of the crankshaft reluctor teeth on here. If there was a damaged one, I can see a broken edge to it. I could see that maybe the whole thing is chipped in half. This is where a lab scope is really going to shine in comparison to scan data. There's times where I may actually want to look at, hey, is this signal going in and out? I'm going to catch it with a lab scope. So now that we've kind of got that covered on the lab scope, Corey, you can go ahead and shut the vehicle off. And we're going to go back over here to the bench, and we'll cover the rest of what we've got to cover. So again, like I said, that's a lot going in through just such a short period of time, but we've got a lot of scan data that we've got to analyze. Again, the trouble codes will lead us in a very good direction. A lot of the time the scan data is going to tell us what's wrong. There are times though where we're going to need that lab scope to analyze, let's say we've got a magnetic reluctor or a slightly damaged reluctor where it kind of comes in and out and we've got a erratic signal. That would be a great example where a lab scope is almost preferable to a scan tool. Now there are some other key points that I want to make though. So let's go back to the PowerPoint slide a second. I'm going to show you something. When we're replacing all of the timing components, I've got the picture on the screen here, and we can go back to the bench now and I'll talk to you on screen. But we've got all of the components. We've got the phasers, we've got the VVT solenoids, and we've got any of the other solenoids that we may have. Now, one of the things we want to keep in mind is when we're doing this is a really big job. I'm sure most of you are aware of that. When we do a timing job, some of the time we're actually taking the engine out of the vehicle to get this timing cover off. We could be anywhere from 10 to 20 some hours to do a timing job. The last thing I want to do is have a comeback after that. And so what we recommend is replacing all of the components related to that. I'm going to do the camshaft phasers. I'm going to do the crank gear so I don't have a correlation fault. I'll do the timing chain. I'll do any of the guides, the tensioner for it as well, and the solenoids. Now, one of the things I want to talk about with solenoids too. We've got some examples laid out here. And if you look, some of the OE samples out here actually, they started off with plastic screens on the VVT solenoids. After a time, these things start getting hot, they wear out, they get brittle, and they can actually break, clog some of these passages, and we have issues with the phaser actually sometimes sticking because the VVT solenoid is not releasing or sending oil pressure the way it's supposed to. Well, we've revised some of this with some of our VVT solenoids, and we'll actually have what we do is a metal screen. Here would be a great example where we've got a metal screen in place of where it used to be a plastic screen on the VVT solenoid. So that's, again, do all of the components on there. We don't want to have a comeback. We want them all to mesh properly and make sure we're using quality components. And luckily, we've got plenty of them here on the bench too. Another thing to keep in mind is when we're doing all of those components, there are some follow-up procedures at times. Again, referencing back to the PowerPoint. If we look at the slide we've got here, so we've got a 2012 Ford Edge, and on the full timing chain replacement, as one of the last steps, it tells us to do a crankshaft relearn or a neutral profile relearn. And what it's going to do is determine that, okay, this is where everything sits, this is our zero position, because misfire calculations are actually driven off of the crankshaft signal. If we don't relearn this, a lot of the time we're going to have random misfire code setting from that. And so we want to make sure we take care of that by doing any relearn procedures that we need to do after all of the repairs are done. So with that, we've got some additional resources we want to cover really quickly. If you go to our YouTube channel, our standard brand YouTube channel, you'll find all of the different tips on, we've got a lot of stuff on VVT, solenoids, replacement, what our best practices, little short videos on all of these different components and replacements. And also, we can find a lot of resources on the standardbrand.com webpage. So we've got a lot of our training insight here, and we can actually access our power hours that we're on right now. Obviously, you've probably had to register for this situation for the one that we're in today. And if you need to go to any previous sessions, we actually have the recorded sessions there too. So feel free to jump back in previous sessions and look through those. They're a good lunch and learn session for you. So you can do a power hour session that we've already recorded even. So with that, I'm pretty much wrapped up with what I've got to present with. Corey, do you have any other questions for me at all?
Yeah, you know, Chris, we actually had a couple things come through. I tried to answer as much as I could, but there were two that I guarantee you are on other people's minds. So I'm going to go ahead and throw those out to you.
Sure.
The first one being, and I know we've dealt with a lot of this here, we've worked on a lot of this here, on those 3.6 Pentastar motors that have four actuators or whatever, actuators. What is the recommendation there? If, let's say we have one we know has failed, maybe two, are we going to be okay if we leave the other 1, 2, or 3? Or
Yeah.
is it one of those things where we're really shooting ourselves in the foot if we don't just go ahead and do all 4?
Right. Yeah. It kind of goes back to, we're covering it earlier, right? Where when we get into this, we're normally diving in pretty far. So especially if we're going down the road of phasers, I know I've seen a lot of, followers fail on the 3.6s. So when we have failures internal to this, we've got a lot of debris going around sometimes. And so I would recommend doing all of whatever we're doing when it comes internal to this. So if we're doing phasers, we're going to do all of the phasers. We're going to do the chains and guides, tensioners, the crank gear if that's involved with it also. And then if we're doing the VVT solenoids, for instance, let's say we've got a failed VVT solenoid, and then now I'm going to replace that solenoid. Do I choose just one or do I choose both? Well, if this one only made it, 80,000 miles or 120, something like that, I'm thinking that the other one's probably not too far behind because they're built quite similarly. So in my opinion, I'm going to be doing both at the same time.
I mean, I was going to say the same thing, Chris, in the chat, but at the same, I just want to make sure it's set on screen by the professional here.
Right.
So, but okay, so here's the second question I want to throw out to you before we wrap it up here, because I know this is probably on a lot of people's minds. With the recent developments and the GM, we'll call it oil gate, whatever you want to call it, where oil change, the intervals and the weights and all that have been changed. All right, so let's say I didn't have a problem yet. I didn't have one of the recalls, but my vehicle's under that, that whatever change. Am I going to be okay, or do I need to preemptively replace my VVT solenoids, things like that, or it just kind of roll until we see what happens with these new oil changes?
Yeah, I think we're probably going to have to kind of roll with it. It's a hard sell also, like especially coming from our side, right? Where being a technician, it's gonna be hard to prove to a customer that, okay, now we're going to have to replace these things. When that's what they've followed all along was that kind of oil change interval. I will say it's good to maybe let the customer know though that, if we've changed oil weights and we've adjusted from one to another, that, hey, we just ran these components with a different oil weight for quite an extended period of time. So there may be some damage done if they all of a sudden have changed things along the line. And it's good to probably let the customer know, right, that, hey, just to let you know, we're running a different weight oil or we're running a different, consistency to it. And if we are, well, things may change. And yeah, there may be some extended wear to some of that as well. And we may be seeing some faults down the road, which a lot of us have seen some of those faults.
All right. Well, Chris, in the spirit of time, I'm going to leave it at that. But I'll say thank you for your answers on that and let you wrap us up here.
Yeah, sounds good. Thank you very much for attending today's Power Hour on VVT Diagnostic Tips.